Chem 1401 Practice Midterm 2. Question number 1 asks us to predict the charge on a magnesium ion. So magnesium, the element magnesium, is found in group 2A. And you would remember that elements that are in group 2A like to lose 2 electrons. So if I have neutral magnesium metal and it loses 2 electrons, so if it loses 2 electrons, what I'm going to be left over with is magnesium 2+. So the answer is the 2+ ion for magnesium. Question number 2 asks us which of the following choices correctly represents the ionization of potassium. So potassium is going to lose 1 electron to become potassium plus. So we have the potassium, it's going to end up losing an electron because it has 1 valence electron, so it'll lose that electron. So if I take a look at what would be the best answer here, it would be this one, because the electron configuration of potassium is argon 4s1, and then I form my potassium ion, and then what's left over is the potassium ion plus an electron. So there we go, the second choice. Question 3, which one of the following salts is composed of isoelectronic cations and anions? And if you remember, isoelectronic means the same number of electrons. So what we should do is determine the number of electrons for each one of the cations and anions for all of these ionic compounds. So let's make a little table here. So we'll tally up the number of electrons in each one of these cations and anions. So for cesium, I form the cesium +1 ion, and cesium itself has 55 electrons. So the cesium cation will have 54 electrons. For chlorine, chlorine is element number 17, but chloride, so that's chlorine with a -1 charge, that's going to have 18 electrons. So that's not the answer. If I move on to the next one, calcium itself has 20 electrons, but the calcium 2+ ion will have 18 electrons. And then my chloride, I already decided that has 18 electrons, so that must be the answer right there. So if you take a look at the number of electrons in sodium, in the bromide ion, I have a total of 10 electrons and 36 electrons. Then for scandium nitride, if I do the same thing, I have 18 electrons and 10 electrons. And then for aluminum sulfide, I have 10 electrons and 18 electrons for the cation and anion respectively. So the answer is calcium chloride. Both the calcium ion and the chloride ion have 18 electrons, making them isoelectronic. Question number 4. Which of the following correctly ranks the ions calcium, sulfide, potassium, chloride, and H+ in order of increasing size? Well, I think it's pretty obvious that H+ is going to be the smallest one of these, because H+ is nothing more than just a proton. So that kind of limits me to these choices here. So I'm going to have my hydrogen ion is the smallest one of these ions. Now if I look at all the rest of these, I'm not going to spend a lot of time on this, but you can see that all of these are isoelectronic with argon. So all are isoelectronic with argon. And what that means is they all have 18 electrons. So then all I have to do is compare the size of the ions. So if you remember what we spoke about in class, we know that anions are going to be larger than cations, and the more negative charge that we have on our anion, the larger it's going to be. So that would make sulfide, the anion with the biggest negative charge, the largest of those ions. So that means that this one must be the correct answer. And if you think about it also in terms of my cations, if you remember that every time I remove an electron, the cation gets smaller and smaller. So that means that calcium 2+ is going to be smaller than potassium plus. This next one is kind of an interesting one. It says the image below shows a compound. So there's the compound or the sample suspended between the poles of an electromagnet, okay, with the mass of the compound balanced by the masses in this balance tray over here. What can be determined about the compound if the balance tray containing the masses rises when the magnetic field is turned on? So what that means is that when the electromagnet here, when this is turned on, so they plug it in, okay, and they turn it on, and what happens is this sample is being attracted in between the two poles of the electromagnet here, and therefore the mass is going to be going up because it tells us that the mass is going to rise. So what that tells us is that the sample is being attracted to the magnet. And you would remember that when we have something that's paramagnetic, that means that it has unpaired electrons and it's going to be attracted to a magnetic field. So paramagnetic means, again, that we have unpaired electrons. So if I take a look at the possible answers, well, the second one here says the sample compound has unpaired electrons. So if it has unpaired electrons, that means it's paramagnetic, and that means that it will be attracted to the magnetic field, causing the masses to rise. So it's a good idea to know what paramagnetic and diamagnetic mean. Question 6 asks, which of the following molecules is expected to have the greatest bond length? So if you take a look at the Lewis structures for each one of these, well, you can see that these ones here, bromine, fluorine, chlorine, and iodine, those are the halogens, right? So if I just draw the Lewis structure of iodine, or I2, it looks like this, and I have similar Lewis structures for bromine, fluorine, and chlorine, and hydrogen. That's the Lewis structure for H2. So each one of these molecules has a bond order equal to 1. So if I want to think about, okay, well, if they all have the same bond order, well, how would I know which one is going to have the greatest bond length? Well, also, you would remember that bond length is going to be related to atomic size. In that, the greater the size of the atom, the longer the bond length, because the atoms are going to be further and further apart. So which one of these has the largest atom? Iodine, I2. There's the answer. The next question asks us, what is the formal charge on the chlorine atom in the Lewis formula of a chlorate anion, ClO3-. So the best thing to do here is to tally up the total number of electrons in chlorate. So I have 7 valence electrons for my chlorine. Oxygen has a total of 6 valence electrons, but there's 3 of them. So 3 times 6 is 18, plus 7, plus 1. So that gives me a total of 26 electrons. So my chlorine is going to be my central atom here with the oxygens surrounding it. So if I start drawing bonds to my oxygens like that, and then if I start filling up all of their octets like that, well, so far I've used up 8 times 3, so a total of 24 electrons. So that means I have 2 electrons left over, and I'm going to put them here on my chlorine, on my central atom. But the problem here is that there's too many formal charges. I'm not going to draw them all in, but chlorine right now has a formal charge of +2, and all of the oxygens have charges of -1. So is there a way that I could eliminate some of these formal charges? And the answer is yes. So if I take 2 of the lone pairs from those oxygen atoms and I convert them into double bonds like this, that means that this oxygen and this oxygen will have a formal charge of 0, and this oxygen will have a formal charge of -1. So the formal charge of my chlorine atom is calculated like so. Chlorine has 7 valence electrons. I subtract the total number of bonds, which is 5, and the total number of unpaired electrons, which is 2. Therefore, the chlorine has a formal charge of 0. Question number 9, which of the following correctly depicts the resonance forms of the carbonate anion? So the first thing we could do is draw the Lewis structure for the carbonate anion. So if I put in all my lone pairs, the 2 oxygens on the bottom both have negative charges. The other carbon and the oxygen with the double bond, those both have 0 formal charge. I'll leave those out for now. But what you can see is that I have the double bond shown here at the top. But we know that based on resonance, that double bond is not localized between that carbon and that oxygen. We know that it could also be between this carbon and this oxygen, or between the carbon and this oxygen. So therefore, there's 3 resonance structures for the carbonate anion. And those are depicted right here in the third one. So this is the correct answer. Consider the hypothetical molecule MZ2. If the elements M and Z have different electronegativities, what condition must be met in order for the molecule to have no dipole moment? So M is going to be my central atom, And if I have my two Z atoms like this, if they have differing electronegativities, let's say, for example, the Z atoms, let's say they're more electronegative, so I would have a dipole going this way and a dipole going that way. Well, the only way I can get those dipoles to cancel out completely is if the molecular geometry is linear. So the bond angle here would have to be 180 degrees. So the answer is the first one, that the molecule must be linear with M as the central atom.